we propose an embodied system called MP5 that can solve long-horizon open-world tasks in human-like ways. Previously, the LLM agent in Minecraft ignored the real-time image observations obtained by the embodied agent and assumed that the agent obtained all the information to make planning, which is obviously impossible in the real world. Firstly, we will show an example. This is the process of finishing the task: kill a pig with a stone sword during the daytime near the water with grass next to it. To achieve the final goal, 08, kill a pig, a player should accomplish a list of sub-objectives 01 to 07 sequentially. During this process, the agent should also be aware of some items in the environment using the ego view visual observation of the agent, for example, park, grass, day, and etc. This exemplar process tells that such long-horizon open-world embodied tasks in Minecraft should be solved both in the process-dependent and context-dependent way. To tackle the challenging open-world embodied tasks in Minecraft in the process-dependent and context-dependent way, we introduce MP5, a novel embodied system contains 5 interacting modules developed within Minecraft to meet the above expectations. Notably, MP5 includes an active perception scheme by means of multi-round interaction between percipient and patroller, which is to actively perceive the contextual information in the observed images with respect to various queries raised by planner and performer. Extensive experiments prove that MP5 can robustly complete tasks needed for long-horizon reasoning and complex context understanding. Let's have a look at our technical design. Let me show you the overview of module interaction in MP5. After receiving a high-level task, MP5 first utilizes the parser to generate a sequence of short-horizon sub-objectives as a list of rich instructions in natural languages. The feasibility of the generated sub-objectives is augmented by retrieving an external knowledge memory, for example, online wiki, user tips, and etc. To one sub-objective, the planner schedules the action sequence that is grounded by the environmental information gathered by the active perception scheme. In this case, the performer will execute the actual actions by explaining the action sequence that is adapted to the embodied environment via frequent interaction with the active perception scheme. Once there are execution failures, determined by patroller, planner will reschedule the action sequence of the current sub-objective, or even update the following sub-objectives if some necessary sub-objectives are missing. Otherwise, the agent will go to the next sub-objective and schedule new action sequences, whilst the successful action sequence of the current sub-objective will be stored in the external memory of the planner, called performer memory, along with the agent situation when it was planned. In the end, the agent will stop when the final sub-objective of the task has been reached. Here is a concrete example: kill a pig with a wooden sword during the daytime near the water with grass next to it. Used to show the detailed process of module interaction. When a sub-objective, killing a pig, is passed to the planner via the parser, the planner asks the patroller for task-related information in the current scene, and then uses the current scene information and sub-objective to generate an executable action sequence to the performer. When the performer completes the equip action, it begins to perform the scene strongly related find action. The performer asks the patroller if it can perform the next action, but since there is no river next to the pig in the current environment, the performer needs to continue the find action. After a multi-step search, the agent finally finds a scenario that meets all the criteria, so the performer is told it can perform the next action. As we know, both perception-aware planning and execution rely on the active perception between the percipient and the patroller. So let me show you the process of active perception scheme. Temporary information set saves information collected in the current scenario, so it should be reset at the beginning of active perception scheme. Performer then invokes patroller to start asking percipient questions with respect to the description of the sub-objective and the current execution action round by round. The responses of percipient are saved in the temporary information set and are also gathered as the context for the next question answering round. After finishing asking all significant necessary questions, patroller will check whether the current execution action is complete by analyzing the current sub-objective with perceived environment information saved in temporary information set. Therefore, complex context-dependent tasks could be solved smoothly. We build a dataset and design MineLLM as the core component of the percipient. Firstly, we collected, selected, and processed the corresponding perceptual information from the simulator that aligns with the EgoView image data, including the blocks in the field of view, creatures, weather, occupancy around the agent, etc. Notably, we specially processed and filtered the perspective information, retaining only the information that can be obtained visually to ensure the requirements of the embodied scene. Based on the EgoView images and perceptual information, we constructed image-text question and answer pairs. To not limit the interaction form between the percipient and the patroller, and to make the interaction more flexible and robust, we designed templates for single-turn dialogue, multi-turn dialogues, and captions. For each piece of perceptual information, we also designed multiple forms of questions and answers, greatly reducing the probability of interaction failure between the percipient and the patroller. The total number of instruction data pairs is 500K. This dataset is used to train our MineLLM. The model architecture is on the right side. Images are processed by a frozen vision encoder, MineClip, whose features are projected by an alignment net to the same feature space as the text embeddings of the applied LLM. Then the vision and text tokens are concatenated to feed into a LoRa-based fine-tuned LLM. We add LoRa parameters to all projection layers of the self-attention layers in the LLM. Only the parameters of the alignment net and the LoRa module are optimized during training. Here are the corresponding screenshots for the dialogue of task, find one sheep on the plains, and the corresponding screenshots for the dialogue of task, find one sheep on the plains, while replanning. More experiments and ablation studies can be found in the main paper, and more demo videos can be found on the project website. Welcome to contact me if you have any questions. Thanks for your attention.